first example as soon as I find it. Oh, there we go. All right, so pretty simple idea here. We have the derivative of some unknown function y with respect to the independent variable x is apparently equal to this mess. And of course, one giveaway that this is going to be homogeneous is that if you look at the combined powers of all the terms on the right-hand side, right, you get x squared and y to the power 1. We have y cubed, we have x to the 1, y squared. All those, the combined degree of any one term there is 3. So it looks like that might be homogeneous. So I would just divide, let's say, by the highest power of x, so x squared. Or you just break that up into two separate fractions even. Maybe that's better. We have a single denominator, so I might as well break that into two separate fractions fairly easily. Yes. Somebody have a question? All right. So this is going to be x over y minus y over x. So indeed we see that if we think of this as 1 over y over x, this is y over x, the right-hand side over here is a function of the ratio y to x. So the natural thing to do, and that's in quotes I guess, but would be just to lump the y over x into a single new variable. So we're going to let, as the flowchart indicates, this is a standard change of variable. We're going to let a new variable be y over x. Right. And so it's the same thing as saying y is x times z. Where did the y prime and the x prime go? I don't know if I understand the... Oh, okay. So, so this isn't prime. This was to the power 1. I was just indicating that the combined degree of any term on the right-hand side was 3. The same degree everywhere, so it was homogeneous. Okay, so now is the change of variable part. You have to remember that, it's good to remember that x is the independent variable. Y is a function of x, and when we define z this way, okay, this way, we see that z is a function of x ultimately, right? So that's important to remember because when you differentiate y here with respect to x, you realize that you have x times a function of x, so you do have to use the product rule, right? So differentiate x times z plus x times the derivative of z, and since we don't know what z is, we just call that z prime. Okay. All right, so now it's just a direct substitution, I suppose, right? If I rewrite the original as y prime is 1 over 1, y over x. We can see that we can just directly substitute for y prime. And on the other side, we have y over x we defined as z. Okay. All right, now if you have a homogeneous differential equation and you use this standard change of variable, then you're guaranteed to get something that's separable, right? That is to say, you can bring all the z stuff to one side and all the x stuff to the other. So maybe I should, well, that's convenient. Notice that z cancels on both sides. And we're going to rewrite the z prime as the derivative of z with respect to x. And it's, this is not a integration competition here, so it's pretty simple. So we separate the x's and the z's. We have two differentials now that are equal, so the anti-derivatives should be equal as well, up to a constant. How does y over x become z? Oh, right. So that's the whole point of a homogeneous differential equation, right? We were able to write y prime is equal to, and on the right-hand side, we were able to express everything as a function of y over x. So we decided that y over x should be called a new dependent variable. We decided it should be called z. Right. So anytime I see a y over x, I replace it with a z. Okay. I hope that answers the question. Now you got me confused there. Oh, you got me. You got me. You're saying over here this should be a minus. Okay, you're right. So no cancellation. It's too bad. I thought I was going to be especially simple, right? All right. Okay, so we're going to subtract the z over to the right-hand side because our purpose is to get all the z's together. Maybe find a common denominator here. And then bring all the z business to the left-hand side. And all the x business to the right-hand side. And then anti-differentiate. Okay, so this should give you, on the left-hand side, it's a substitution. It should give you a log of some sort, right? So it'll give you log of 1 minus 2z squared. And then negative 1/4. All right. Right, so then it's just, of course, we're not done. Let's not forget to, let's try not to stop at this point because we do want to know what y is, right? So I'll just multiply everything by -4 and exponentiate. To get rid of the logs. Over here, we're going to get right, x to the 4. So just get x to the 4. And just be careful over here, right? This is properties of exponentials. You get e to the log, e of log, and then times e to a constant. We lump this together into a new positive constant. Call it k. And the absolute value doesn't matter because since z is a arbitrary positive constant, we'll get plus or minus k, which is just an arbitrary constant. So all that noise is just to say, I guess the absolute value didn't really matter. All right. Great. So now it's just a matter of back substituting, and so we know that z is really y over x. And that's pretty much it. Here you at least get an implicit solution, right, for y. You have an equation relating x and y that satisfies the original differential equation. If you wanted to, you could solve for y, I suppose. You might want to, I guess. Yeah, so if I solve for y, unfortunately, this is not uh, exactly what we want, right? Because we have plus or minus, y is equal to plus or minus something, and it's not both, it's one or the other. And so that's going to be based on initial conditions if you have one. So if they say, I guess, y of 1, I suppose, is equal to -2, right? So that's an initial condition. Right now we have, if you'd like, a family of solutions. So we have a general solution to the differential equation. Using the initial condition will let us to pick out the, does raising e to the log cause the negative? Uh, oh, yeah, so, oh, you're saying that that should have been x to the, yeah, you're right. So this should have been e log to the x, or -4, so that's x to the -4. So 1 over x to the 4. Yeah, you're right. It's okay. We'll just fix that real quick. I'm glad you're here. Okay. Do we have to reduce the power of y and x functions before plugging into reduce the power? I'm not sure what that means. Oh, if you know it's homogeneous, yeah, you can just go for the substitute, the substitution, right? Y is equal to x times z right away, if you know. Anyway, right, we have a solution curve, and it's a general solution because of this arbitrary constant k. And then you can use the initial condition to pick out a particular solution to the initial condition problem. So when x is 1, right, y is a function of x, so this notation indicates that x is 1, y is equal to -2. Okay. So we get that k must be -7. All right. And then you can get a particular solution. Okay. So that was an example of homogeneous, if you recognize it, right? Um, we have the standard change of variable, or if you'd like, y equals x over z. Don't forget to use the chain rule when computing y prime here. Yeah, sorry, the product rule. All right, and that substitution will give you a separable differential equation. Okay, there was another problem on your for problem review or practice exam 1. That was a shift to homogeneous, this kind of thing. Right, so it's a differential equation that's almost homogeneous, except we have some constants that we want to get rid of by doing a shift of variables for both x and y. So we'll do an example of that. So what's going to happen is we're going to do a shift, so our differential equation becomes homogeneous, then do the standard change a variable for a homogeneous differential equation, which is going to in turn it into a separable differential equation. Okay. So let's do that. Um, I'll try to be more careful this time. All right, so this might look like okay. So this is going to be our next example. Uh, so it's almost homogeneous if you didn't have those constants. Maybe we see this more often as if we rearrange stuff and write it as the derivative of y on one side, and then just move all the stuff to the opposite side. So all right. So here the idea will be to get this to be homogeneous, right? If you just imagine if I temporarily just erase these constants, this 1 and 4, you would have something homogeneous, right? If you divide the top by x, you would get 2 plus y over x. And on the bottom, if you divide by y as well, you get y over x minus 1. So that's homogeneous because this is a function of y over x, not just, not just any function of y and x, but the ratio of y over x. So to get a homogeneous equation there, we're going to shift. So we're going to take the old variable x and name it and let it be a new variable. Let's just, we could use x bar, x tilde. I'll use uppercase x, and then plus some shift, some h, some constant. And y also is going to be shifted. Now, these constants, this h and k, there are going to be some constants that will get rid of this 1 and 4 after we do the substitution, right? So first of all, notice that dy is just d big Y, right? Because that's a constant. And dx is just d big X. So the left-hand side doesn't change because you're just adding constants to the new variables to replace the old ones. So on the left-hand side, that's not a problem. On the right-hand side, if we replace x and y, the denominator as well, okay, what you want to do is, well, gather the variable stuff, and then gather the constant stuff. And the purpose here was to get this constant to be 0 and this constant to be 0, right? So that way we get a homogeneous differential equation. So that gives you a system of two equations, two unknowns. So we want 2h plus k plus 1 to be 0, and k minus h plus 4 to be 0. And then you solve this system, whichever way you've learned. It's two equations, two unknowns. You can use high school methods or you can use linear algebra methods. I guess I'll use, I don't know what that's called, high school method. I'll just subtract one equation from the other. Right, so apparently h is 1. And if h is 1, then k must be -3. All right. But that's it, right? We just save that and put that in our back pocket that we let x, the original x, be big X plus h, and we let little y be big Y plus k. Let's put that in our back pocket because it's already done its job, right? We've chosen h and k, so these constants become 0, and now we have a homogeneous differential equation. Divide the top by x, divide the bottom by x at the same time. Right? Great, great. But then, of course, we got to go through, let's let a z equal y over x. Or, better yet, yeah. And then differentiate using a product rule here. Remembering that z is a function of x ultimately. And that's a direct substitution, right? We get on the left, y prime is replaced. On the right, y over z becomes, sorry, y over x becomes z. And this homogeneous differential equation after the change of variable is guaranteed to be separable. So let's see if that's the case. Common denominator. And now we can separate the variables. Plus c, sorry, that's a plus c. Yeah, so I hope I don't have to do partial fractions, but it looks like I might, unless... Oh no, a substitution suffices. So two differentials are equal. The antidifferentials are equal up to a constant. So this looks like it's some sort of log. Okay. Is that correct? 2z? Yeah, that's correct. I mean, I don't want to prolong the pain of doing antiderivative or integration there, but all right. And yeah, anyway, we're just going to get a relationship between x and y here, an implicit solution, right? So after exponentiating both sides, we just don't want to forget to replace z. Okay. And so that's a general solution. It's an implicit solution. Awesome. All right. So shift to homogeneous. You know, it was on your paper exam review, so I thought I would do an example. All right. Let us go back to the flow chart to see what's next. All right. So next we're going to have a first order linear differential equation. We'll go over an example just because we do need to know the procedure for that. But they'll usually roll that in because if you have what we call a Bernoulli, right, which is not first order linear, but almost. If after a certain change of variable, you will get a first order linear differential equation, so they could kill two birds with one stone, so to speak, right, by just giving a Bernoulli. Let's see if I have a fairly straightforward example of a linear so we can go over the procedure. Yeah, this should work. All right. So we're going to do an example of first order linear really quick. All right, so the idea is that you want to, this is being recorded and I will post it on Peer Tutoring's YouTube channel. So it'll take like a couple hours for it to process and stuff. I can post the link, but it's just go to YouTube and search for Peer Tutoring or UT Dallas Peer Tutoring. Okay, so we're going to y. No, it's first order. The first order refers to the highest derivative of y, or the highest derivative of the dependent variable. So here it's all just y prime, right? Second order would involve y double prime. Third order would involve y triple prime, right? So for most courses that I see, like for applications of this course, right, it's first order and second order mostly in practice, undergraduate career. All right, number one, first order linear. So you want to write it in conventional form. So you want to make sure that y prime is has a coefficient of 1, right? So if there's something multiplying y prime, you want to make sure you divide by that. All right, and then we have some function of the independent variable. Let's call it x. And that's times y, and that's equal to some function of x on the right-hand side. Right. So after you write it in this conventional form, you identify the integrating factor. So I guess everybody calls it mu, and it's going to be defined as e to the antiderivative of p. And that's why it's important to write your equation in conventional form so you correctly identify p. Okay. As a note, the reason all this stuff works is that if you differentiate the integrating factor, you're going to get it back because you're differentiating an exponential. Chain rule then says you have to differentiate the anti-differential, so you just get back the thing you're integrating. So, but that's just that's not as important, except for theory, right? So then next you would multiply both sides by the integrating factor. So both sides of the original differential equation by the integrating factor. By design, notice that we have mu times p, which is equal to mu prime. So the beauty of this procedure is that you force, like it's the left hand side is the product is the result of the product rule on the integrating factor times y. Okay. And then of course to solve for y we would unprime the thing, so we want to anti-differentiate both sides. And don't forget the constant of integration. And then finally you divide by y. So some people kind of skip the part 3. If as soon as they know how to identify the integrating factor, they know that at the end of the day, y would be equal to this, right? You have to divide by mu over here, and you then you have to find the antiderivative of integrating factor times q, and don't forget the c, right? The constant. So standard conventional form, so identify p correctly, compute the integrating factor, and at the end of the day, unless you want to go through the process of step 3, you can, or maybe your grader expects you to, I don't know, step 4. All right, so here is an simple example. So we have cosine x y prime sine x y equals 1. All right. So this is not in conventional kind of form because y prime, right, doesn't have a coefficient of 1. It's being multiplied by cosine, so I would just divide everything by cosine. This way we've correctly identified p as the function of x that's multiplying y. The antiderivative of p is log of secant. I'm going to assume that x is between negative pi over 2 and pi. Okay. So if you don't know how to get that, for that antiderivative, I guess I should just say it. It's a u sub. U is cosine. Right. So after you do that substitution, you get like the negative of 1 over u, and that's negative log. It's a negative log of cosine. But then I just use properties of logs to bring the power of negative 1 inside, which gives you the reciprocal of cosine, so that's log of secant. Anyway, all right, so then our integrating factor, that's step 2, would be e to the antiderivative of p. So that's e to the log of secant. Right, that is to say it's just secant. Okay, so now we've found the integrating factor. We can multiply both sides of our original here by that. Oh, let's just think of secant as 1 over cosine, I guess. Might be easier. All right, so you can double check that the derivative of the integrating factor is exactly sine over cosine squared, right? Just to double check. So the derivative of that would be negative cosine to the negative 2, and then times the derivative of cosine, which is negative sine. Yeah, that's right. So this means that the left-hand side is just the result of the product rule on the of the integrating factor times y. Okay. So next we simply anti-differentiate both sides. On the left, it's just going to d-prime the sucker. And on the left, well, it's the antiderivative of secant squared, and we all know that that's equal to tangent, I believe. Right, the derivative of tangent is secant squared, so up to a constant. So finally, divide by the integrating factor. In this case, it's, I guess we just multiply by cosine x on both sides. Pretty simple. So that's your general solution. Right, if you have initial condition, let's say y of 0 equals 1, that's easy enough to get a particular solution. X is 0, y is 1. So it looks like C is equal to 1. All right, so your particular solution would just be the sum of sine and cosine. So particular solution. Okay, but anyway, that's the basic mechanics of solving a first-order linear differential equation. Standard form, identify P, compute the integrating factor, and then that'd be your solution. All right, but now let's get to the more interesting stuff, right? So Bernoulli, we said, is professors like because they get to test you on first-order linear differential equations as well when they do that. So let's pick a Bernoulli here. This one looks good. Yeah, all right. Okay, so what is a Bernoulli? I know it's a review, so you all probably know. But it's if you write it in kind of conventional form, right? Like this is first order linear, right? But as soon as on the right-hand side you have some power of y as well, it's no longer linear in y, by the way, right? It's not even linear, but it's Bernoulli if you can get it in this form. Does anybody remember the standard change of variable? When you see that you have a Bernoulli differential equation there? Okay. Well, thank you. It's like a rhetorical question, I guess, but thanks. So z is equal to y to the power of 1 minus whatever n is. All right. Now, well, let's do an example because I wanted to go over the two ways to complete this change of variable. One way is indirect substitution. The other one is direct. So maybe I can do a simple one just to demonstrate that. Yeah, let's do a really simple one. All right. So let's consider y prime minus 4y. All right, so this is already kind of written in standard form. So that kind of makes it easy. But we identify the power, for y on the right-hand side as a half. So z we would define as y to the power 1 minus a half. Okay. All right. So the first method that people use to complete this change of variable is a direct substitution. Okay, and that just means you want to solve for y first. So we see that if z is equal to square root of y would be equal to z squared. And then you can compute y prime, remembering that, since y is a function of x, so is z. So you have to use the chain rule there. Okay. And this is called direct substitution because now you're just free to replace y prime, right? And then you're free to replace y directly. So y prime would be, sorry. All right, so y prime is equal to 2 times z prime. Y is z squared. And y to the half, right, is z. Okay. All right, so now we're just gonna, so this change of variable for Bernoulli guarantees a first order linear differential equation. So to get it in standard form, I'm gonna have to divide both sides by 2z. Uh, and indeed, right, we get a first order linear differential equation in z. Okay, now, so the other method is the indirect substitution method. And it's really a matter of just like what you feel comfortable with. So indirect just means that, well, we don't solve for y. We're simply going to just compute z prime. So you power rule and then times y prime, because y is a function of x. Right. So then people look at the original and they say, well, okay, well, here's y prime. So I'm just going to introduce the factor that I need in my original differential equation just by multiplying everything by that factor. So I'm going to multiply the left and the right over here by the missing factor on both sides. So yeah, I don't want to abuse notation, both sides. All right. Right, multiplying these guys just gets you y to the 0. All right, so now we can just do the, indirect substitution where we see that this guy is exactly z prime. Y to the 1/2 is it'll turn, I mean, if you do this direct substitution, this kind of pattern always happens. It'll just, whatever you get there, just becomes z. Yeah, so, right. So I don't know which method you were taught. I'm kind of curious, or which way you tend to do this, a direct substitution or an indirect substitution. Can we use times integrating factor? Yeah. Sure. So let's solve this differential equation. I'll try to answer that question by going to the flowchart really quickly because something standard always happens. So okay. So here we see that the function multiplying z here in our first order differential equation is -2, constant. So our integrating factor is just going to be negative 2x, e to the negative 2x. Okay, so we multiply both sides by it. By design, the left-hand side is just the product rule of z times the integrating factor. All right, we anti-differentiate both sides, not forgetting our constant of integration, and finally divide by the integrating factor. So. Okay, and that's a general solution. Oh, almost made us. But we know that y is, sorry, z is really what? What did we say z was? Where was it? Z is equal to is the y to the half. So this is right. If you'd like solving for y explicitly, you just square both sides. Voila. Okay, so to answer somebody's question here, let me try to see if I can still pull up my flow chart is still on there. Yeah. There you go. So for Bernoulli, if we look at the flow chart here, this standard change of variable that we're doing leads to a very predictable first order differential equation, right? So I'm not sure if I'm going to answer your question correctly, Jason. So here the integrating factor is like so. And yeah, I'm not sure if I can answer your question, Jason. Maybe you learned something in class that I'm just not too familiar with. So you're trying to somehow roll together this change of variable together with the fact that it's first order linear and just do everything in one fell swoop, if that's my understanding. Right. But anyway, I'm not going to try to waste your time by trying to figure stuff out on the fly here. Apparently, I just don't know exactly what you're referring to, Jason. So I'm going to, I guess, leave it at that. But if you'd like, if you recognize a Bernoulli, the change of variable, you do have, like, you kind of know what you're going to get. All right, so that looks awful. So let's go ahead and maybe try to write it in standard form. Let's divide everything by 1 minus x squared. I guess here we're going to assume that x is between negative and positive 1. So let's see, that would become the square root, I guess, of 1 minus x squared. All right, so I just wrote it in standard form by dividing everything by 1 minus x squared. And we see that it's indeed Bernoulli. We get y prime, some function of x times y equals some function of x. And then we have this extra y to some power. So that makes it nonlinear and Bernoulli. The power is -2, so our change of variables should be z equals y to the 1 minus n. So z equals y cubed. So over here, I'm right. If I were to use direct You could do direct. That's fine. Like just take a cube root of both sides, right? And just find y prime and then directly substitute for y prime and y in the equation. I'm gonna do indirect because it just seems more elegant. I don't like fractions. So z is y cubed. Z prime, 3y squared times y prime. So I see that we have a y prime. I need to introduce this factor of 3y squared into my original differential equation. So I'm just going to multiply both sides by 3y squared. With an abusive notation here, I'm indicating you want to multiply both sides. All right, on the right-hand side, notice that we get y squared times y to the negative 2, so that's y to the 0. All right, and then we see that this is exactly z prime. And y cubed is exactly z. And then we have the right-hand side, which is now free of z, so it's no longer Bernoulli. Oh boy. So now we first order linear, right? So our integrating factor is I believe that gives you, let's see, there's a 3, negative 3 halves log. Oops. Yeah, that works. Hmm. Okay, so apparently that's our integrating factor. We multiply both sides by it. So that would reduce to, oh, okay. So it looks like it's going to be partial fractions. Is it sometimes better? Well, I mean, I don't see how this integrating factor is. I mean, what you don't always get a log, right? So when you do this antiderivative of p, whatever, you don't always get a log. So, but if you do, yeah, you might as well just, exponential and log or inverses just cancel those out because it's just simpler. But yeah, sometimes you can't like simplify because you don't get a log when you integrate p. I don't know if that answers your question. Okay. Okay. All right. So yeah. So I mean, I wrote the left side out, but we know what it really is. It's just z times the integrating factor differentiated. So now it's just a matter of anti-differentiating both sides and partial fractions. Oh, yeah. Well, I guess you need to do division first, right? You can't do partial fractions yet, right? To do partial fractions, the degree of the denominator has to be larger, strictly larger than the degree of the numerator. So it looks like we're going to have to do some division. Okay, hello. Okay. So minus x squared plus 1 is dividing, let's do it, 3x squared. I meant negative 3. All right. So you can probably figure that out without the long division, but we have this is negative 3 plus the remainder divided by the divisor. And so now you can use partial fractions here on the second term. It looks like A and B are both 1/2. Okay. Okay. All right. So now we can anti-differentiate both sides. And I guess that's pretty much it. Maybe except cleaning this up by using properties of logs. But this would be log of 1 plus x over 1 minus x. And then, of course, we don't want to forget z is really, what is z? Z is really y cubed. So if you'd like, you can take the cube root of both sides to get the very nasty solution. Okay. No, I mean, there's not a fast way. You just have to know how to, do the partial fractions. Here, I just done it so often that I saw what A and B should be. But I guess if you'd like, we were trying to get this to be the same as the original fraction, which was 1 over 1 minus x squared, right? So you multiply everything by the common denominator, get rid of the denominators in one fell swoop. But I can't think of a fast way unless like there's some ways like with complex numbers that you can do it, but minus 3x. This guy? This guy? That came from anti-differentiating negative 3. Am I wrong? Okay. Anyway, I'm getting that negative 3x from anti-differentiating the negative 3. And I got that negative 3 by doing the division over here, the long division. Okay. Anyway, so that's another example of Bernoulli, but it's 307. So we're, I mean, unless you want to see another one, maybe later. But let's go into the other kind of way of looking at these. Let's see. Let me grab my flow chart. All right. So the other way of looking at these differential equations is kind of in this differential form, where let's see, yeah, where we have some function of x and y multiplying dx. So that's a differential. And then some function of x and y multiplying dy, and that's equal to 0. All right. And the idea is that if we have some function of x and y equal to a constant, and you compute the total differential, you would do it by finding the partial of f with respect to x dx, and then partial of f with respect to y dy. Okay, and if you differentiate this with respect to y next, and you differentiate this with respect to x, if your function, your f function, is smooth enough, then these should be equal because mixed partials would be equal if your function is like smooth. So the idea is that when I took the derivative of this with respect to y, that would be the same thing as differentiating m with respect to y, and then differentiate n with respect to x, right? And if those are equal, we call that an exact differential equation, in which case we can try to recover this original f. And our solution will be in this form. We can call it a solution curve. So let's do an example of something which is exact, and then of course on your test you would get something that's not exact. So we'll review how to fix that by finding an integrating factor. So yeah, this looks good. It doesn't matter. Okay. So this is going to be an example of a exact differential equation. And right, so we identify m here as the thing multiplying the differential dx. We identify n as the thing that multiplies dy. And of course, you want to be careful here in these formulas. There's a plus here in the formula. So you have to think of that as plus and negative cosine. So n would be negative cosine. We're going to check for exactness. So we're going to differentiate m with respect to y, right? It's the opposite of what that is, yeah, x. And here we're going to differentiate n with respect to x. The derivative of cosine is negative sine, so we'll have a double negative. So indeed, derivative of n with respect to y is the same as the derivative of n with respect to x. This is exact. So the thing that we want to learn is how to recover the function f so that we get a solution like that. All right, so there's two approaches here that I know of. Here's one approach. You're just going to anti-differentiate both sides here, right? So you're going to anti-differentiate the left-hand side. And I know the right-hand side is kind of weird, but so here you could be integrating with respect to x. So it's like a partial integration, right? It's that you treat y, the other variable, like a constant. So you're going to get x minus y cosine x. That's the antiderivative with respect to x. And instead of a constant of integration, you're going to get a function of the other variable. So let's say h of y. Okay. And so in a sense, this is your f. Okay. On the other hand, if you integrate this with respect to y, you would get minus y cosine x. And you're anti-differentiating with respect to y, so instead of a constant of integration, you get a function of the other variable not involved in the anti-differentiation, so g of y. And this is f as well. Okay, so we can, by setting, we have the same function, I guess, we can set those equal to one another. And you recognize that h of, g of x, what cancels? So it looks like g of x is x, and h of y is just a constant, or 0 if you'd like. Right, so then plugging that back into either one of these here, we get f is, f is x minus y cosine x plus h of y, which is 0. On the other hand, you can say f is minus y cosine x plus g of x, which is x. In the other case, you get the same f. And so now we can just say that our solution should look like f equals a constant, right? If you'd like, if you anti-differentiate 0, you get a constant. C. So this is our solution curve, or family of solution curves. Okay. So the other way people do this to find f, let's see if we got it here. Yeah. Make sure I write it down correctly. 1 plus sine. All right. So the other way they do it is they realize that this should be the derivative of something with respect to x, right? So the derivative of that something, the f, with respect to x should give you that. No. So remember that we have that f is equal to some constant. That's our assumption. If it's true, then if you take total differential, right, then the thing multiplying dx is the partial of f with respect to x. So we simply then undo this partial differentiation with respect to x by anti-differentiating with respect to x. Right, which gives us, okay, and we don't get just a constant of integration, but rather we get a function of the other variable. Okay. All right, so next people will say, well, I kind of have f, right? I kind of know what f is, not completely, because we don't know what h of y is. But I do know that the derivative of f with respect to y has to equal negative cosine. So they differentiate this in turn with respect to y. And then they set it equal to what it's supposed to equal here, namely minus cosine x. So you, after noticing that the cosines cancel, you get h prime of y is 0. So h of y is just some constant, right? It doesn't matter. So then there we go. F would be up to some constant. I'll just let the constant be 0. And our solution curve would be, okay. So, all right, I don't know what method you were taught to recover f once you know you have a exact differential equation. I have at least two, I guess, two related. Yeah, I mean, it's the same thing, yeah. I mean, if you have enough practice, I think most people just kind of do the first thing. So if you anti-differentiate this, you get x plus y, x minus y cosine x. And anti-differentiate the second term with respect to y, of course. And what people do is they say, well, you just kind of take a union of the terms. Like, so you only use a term, if a term appears twice somewhere, you just use it once. So x appears once, and then this appears twice, but you only write it out once. And that's equal to a constant. That's kind of the quick way once you get used to it. But formally, you might want to go through this procedure. Okay, that's a good case. Yeah, I'm recording it, and it's not going to be on Blackboard. We're just going to post it on YouTube. So h of y equals 0 and not x. I'm not sure what that means. Why would h of y equal x? That would be a contradiction, right? You're saying some function of y is equal to a function of x. Oh, I know where I think I know what you're saying. Yeah. So, okay, it's getting messy in these notes here, but I think you're referring to this, right? So, equating those two, canceling, right? So here, this says that g is a function of x, so it must be equal to this because it's the only function of x. And if that's g of x, this means h of y must be 0, right? I'm not sure. Oh, okay. All right. So let's see. Yeah, let's do some special cases, right? For when we do not have an exact differential equation, and we need to find an integrating factor, which will turn it into exact differential equation. Don't worry about it. It's no big deal. Okay, so if it's not exact differential equation, there are some special cases, and I think, unless they say something, look for an integrating factor of this form, you would expect one kind of these basic things. So if we have that this is a function of, yeah, I can post the chart on the description of the YouTube video. Okay. Yeah. Okay. It might be on the peer tutoring website. I don't even know. All right. But I'll definitely post it in the description of the video. All right. So here, if we don't have an exact differential equation, there are some, especially two special cases that we're going to be aware of, right? Okay. So I'm not going to go through the derivation, but right, if we have that this is a function of x only, then we know our integrating factor is a function of x, given by that. Right? And then if you just, I guess, negate the numerator and then change the n to the m in the denominator, if this is a function of y only, then we have an integrating factor to turn our inexact differential equation into an exact one. Okay. So let's just do some examples. Hopefully this works out. Yeah, so the two special cases I'm going to focus on is that this is a function of x only, and then this is a function of y only. All right. Yeah, by the way, not all of these are like just one type. Like this differential equation that I'm writing down is also a first order linear. So just by rearranging, right, there's kind of two conventional ways. Write your differential equation like this, write it like this in differential form. So sometimes it's just a matter of starting to rearrange stuff until you recognize the differential equation. But if you're interested, you can try to rearrange this to see it's also first order linear. Okay. But for now, we're gonna just, m is multiplying dx, n multiplies dy. So we're going to check for exactness by differentiating m with respect to y, and differentiate n with respect to x. -1 does not equal 1, so this is not exact. So now we're just going to go through the tests, right? So we're going to check if we have a special case for our integrating factor. So I'm going to try nx minus my divided by m. I mean, I'm being stupid, but 1 minus Negative 1 divided by m. Nah, no way. Is this a function of just x? Or I'm sorry, of just y? No, there's no way. So this is not a function of just y, right? 1 second. Okay, so maybe it's the other case. So my minus nx divided by n. Is this a function of x only? N is equal to x, yes. This is a function of x only. So now we know that an integrating factor here goes according to this formula. So we get log of x, properties of logs, log and exponential are inverses. So it looks like our integrating factor is 1 over x squared. And the integrating factor's job is to multiply both sides of the equation here. So as to make the differential equation exact. So multiply both sides by 1 over x squared. And so now I'm going to use m again, but it's a different m than before, right? I could say it's m tilde or something, but I don't want to confuse the issue here. I'm just going to make sure that it's exact, that I don't make any mistakes. I'm going to differentiate m with respect to y. And differentiate n with respect to x. That's right. So now these are equal, so we have an exact differential equation. Okay, so now I'm just going to anti-differentiate. I'm going to find f by anti-differentiating this with respect to x. Okay, that's good. And then for our, instead of a constant, we're going to get a function of integration. That's a function of the other variable, y. All right, so next we differentiate this with respect to y because we know it should equal to n. So we set that equal to n. 1 over x is cancel on either side. So h of y is just some constant. You can just let that constant be 0 if you'd like. All right, so now we have f is okay, plus h of y, which is, I guess we can choose to be 0, and our solution curve is where we just let this to be a constant. All right. Would you like to do another one where maybe, yeah, let's do another one. Sure, so let's do this one. All right. Identify m, which is multiplying dx. Identify n, which is multiplying dy. Check for exactness by differentiating m with respect to y and n with respect to x. 2 is not equal to 1, so it's not exact. So we're going to try to find an integrating factor, and we're going to check for the two special cases. Which I always forget what they are. I mean, like what they look like exactly. So, all right. So we're going to check whether this is a function of x only. I'm going to do that one. Nope, not a function of x only. So we don't have that special case. So now let's flip that around. Yeah, it's a function of y only. Okay, good. Okay, so that satisfies the second special case. So we know our integrating factor is just e to the antiderivative of exactly that expression that we just saw as a function of y only. So that's just y. Kind of boring, but that's our integrating factor. So we're just going to multiply both sides of our original differential equation here by it. So we're going to get y squared. Right, and now this should be exact. The new m, differentiate with respect to y. The new n, differentiate with respect to x. Indeed, these are equal, so it's exact. So now it's just a matter of recovering a function f uh, whose differential is equal to this. Right? So, all right. So, derivative of this f with respect to x should give me m. We recover f by anti-differentiating with respect to x. All right. And we get a function of y as our quote-unquote constant of integration. In turn, differentiate f with respect to y. And that should be equal to, oh my goodness, n. Now notice that some stuff cancels out. Importantly, the x stuff cancels out. Otherwise, we would get a contradiction and we would have gotten something wrong, right? So if I have h prime of y, so we have a function of y, you know, it better be equal to just a function of y. There better be no x's there. So that's a good sign that we didn't make any obvious mistakes. All right, so now to recover h, just integrate both sides with respect to y. Oh no. All right, integration by parts. I'll use tabular method. Epic? Which one? Integration by parts is epic? Yeah, you're right. It's always, yeah. a joy. Okay, so that would be. All right, so that's h of y up to a constant, of course. So now we know f, right? F we said was xy squared plus this h of y, which uh, we found using integration by parts. And that's set that equal to a constant, and you get your solution curve. All right. What time is it? Oh, we have plenty of time. Do you guys want to see anything specific? So we went over homogeneous and how that after a change of variable that gives you separable. We went over to shift to homogeneous, first order linear and Bernoulli, and now exact and inexact differential equations. So I mean that's pretty much it for the first exam, right? Those are the standard things you learn, unless you want to. What was on your review? I don't think there was anything else. Anyway, do you want to see examples of anything else? Homogeneous and non-homogeneous examples, please. Okay. So, well, non-homogeneous is like a broad category because that's everything that's not homogeneous, but I think you just meant homogeneous. Huh, let me see if I can pull out some problems then. All right. All right. Number 2 in the exam review, I don't understand the part of the transformation. Oh, you might have missed the very first problem we did. So this number 2. Oh no, number 2. Are you confusing number 2 with number 1? Because you seem to be referring to Grant. You seem to be referring to two different problems. Right, so that was the shift to homogeneous. The idea is that we want to get something that's homogeneous. So this means that we don't want to have these constants. So we want to end up with like this, right? Because then if you divide the top and bottom by x, you would get on the right-hand side a function of y over x, so that becomes homogeneous. But to do that, we just shift. So we're going to replace the old y with the new y plus some amount, k. And then the old x is replaced with the new x plus some amount. We compute dy, right? Because h and k are just constants, the differentials are going to remain the same. And then we substitute, in particular on the right-hand side, sorry. On the right-hand side, replace the old x and y. So you directly substitute for y and x. So we did this example like this at the very beginning, but It's okay. Okay. Gather all the variable stuff. So the x's and the y's, and gather all the remaining constant stuff. Right, and now the idea is to choose h and k. Choose h and k, so these guys become 0. Right, so that we get our homogeneous equation. All right, so that gives you a system of equations to work with. You have 2k minus h plus 5 should be 0, and 2h minus k minus 4 should be 0. So you solve that system. Let's say multiply the top equation by 2 and add the two equations. So you get 3k, you get 10 minus 4, so 6. So k must be equal to negative 2. Okay. And once we know that k is negative 2, apparently h is equal to negative 1, or 1, I think. Yeah. All right, so this means that the old x, so little x, is the new x. I'm using uppercase. Some people use like x tilde, x bar, something to distinguish it from the old x. So it was big X plus h. H happens to be 1. The old y is equal to the new y plus k. K happens to be negative 2. So that's how they got that shift. Just to get, so you can get a homogeneous differential equation. Does that answer your question about how you got those? Okay. All right. Let me try to find some homogeneous ones. Okay. Hmm. All right, I can't think of any ones at the top of my head. So if dy and dx are together on one side of the equation, example is dy dx equals a function of x. Oh, well, that's an interesting question. Let me decipher it. So you're saying if dy and dx are on one side,